welcome to the podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to talk about colors. So, I was once referenced in a valedictorian speech here at BBCHS as the colorblind man that taught students about color.
And your name is White. I think that's funny, too.
Irony everywhere. Okay? So we're going to talk about color as it relates to light, and we're going to talk about color as it relates to pigments, and two very different things. So I think
the pigment is really the one that everyone knows that red and yellow equals orange.
So we're going to wrap up with that. We're going to do the hard one first. We're going to talk about
light.
Light uses something called the additive color theory. And it was, they experimented with it in their investigation, and they saw it on the What Do You See, that if you had the red light plus the green light, you got yellow. And if you did the red plus the blue, you got
magenta.
And then the only two left are blue and green. You get
cyan.
Like
that bluish color.
And so one way to think about this is if we have red light, or we think about the color spectrum, if we recall, it's red, orange, yellow, green, blue, and violet. And you see three of our primary colors are right up here in red, green, and blue. And what we do know is that on this side of the color spectrum, the red side, we have tiny wave... I'm sorry, I misspoke there. We have longer wavelengths, tiny frequencies. And over here on the violet side, we have smaller wavelengths, but larger frequencies. So what we end up having is, if we go back just for a second, is notice, I wish I could just grab this. Maybe I could just take this with me here. So, nope. So, if I go long wavelengths, that would be red, plus middle of the road wavelengths, that would be green, then I get yellow. If I go long wavelengths, red, plus tiny wavelengths, blue, I get magenta. And if I go blue plus green, or low plus middle, I get cyan. So what happens is that these different wavelengths of light, they interact with each other. Do we have a...
It's really causing interference.
Yeah, that's our physics word. All right, so these colors, these secondary colors, are due to interference, which we talked about way back in section 2, where we sent the pulses of the springs at each other, and on the same side of equilibrium they added together, and on the opposite side of equilibrium they subtracted apart. All right? And so what this allows us to do is take a look at something called a gizmo, an online simulation. And what we can do is we can turn on red and green. And right now, okay, I've got the green turned all the way up, and if I were to mix some red in there, according to the additive color theory,
you should get yellow.
You should, in fact, get yellow.
Just got to get them to overlap.
And when they overlap, is that yellow where they overlap?
Mm-hmm.
If I have total overlap, then I, in fact, get
totally yellow.
Totally yellow. So if a red spotlight were to hit a green spotlight, this is exactly what would happen.
And they should have seen that on the board. When they turned on the green light and the red light, you see yellow. It's a little bit washed out, and our lights aren't perfect, but you can see that.
It would work better if we didn't have any outside light coming in, because especially the red gets washed out. If I turn off the green, of course, and I turn on the blue, okay, our red plus our blue should be
cyan.
Magenta?
Red plus blue. I'm sorry, magenta.
And so I always thought this was purple.
It looks more purplish here. In real life, I think it's a little bit redder than that.
Okay. Now, what's really interesting, and we could do this with any of them, I was talking to Mrs. Bretzloff about how to make warm colors versus cool colors, and that conversation was way over my head.
More red than blue.
Right, so what if I peeled the blue back, and now I've kind of got this, I've got a cooler looking color or a warmer looking color, however that works. Or I could amp up the blue, and I could turn down the red.
So it's a colder.
Right. And so there's a lot of things that can be done here. We could turn off the red, turn the green back on.
Now we have cyan.
We get that cyan, and we could adjust accordingly. And another interesting person to talk to in the building about this would be Mr. Turner, because he's the director of the auditorium.
Right, so lights make a big difference on the stage.
Right, so he has the ability to make the stage look like it's a sunny day or a sunset or evening with moonlight. There's a whole bunch of things that can be done. But if you really want to see what happens when we have all light, then you turn all three on.
Right in the center there we can see white.
Yeah. And so you can make any color of light with red, some combination of red, green, and blue.
And what technical device in our home does that?
Well, I don't know which one.
TV,
Oh,
RGB monitor.
Yeah.
That's where the RGB comes from.
The red, green, blue.
Right.
And then when you pay attention in class, when the projectors first turn on, like if the computer input is on, in the lower corner it says RGB.
Right.
Photoshop can be set to two settings. One setting can be RGB, so if this is light, then that's the setting on Photoshop that you want. If it's pigments, then you set it to the other setting, which happens to be yellow, magenta, and cyan.
Right.
And something really interesting happens. When we start talking about pigments, we don't use the additive theory, we use the subtractive theory.
And I asked my class, so where would you go and buy cyan, magenta, and yellow to make something? And it's a printer cartridge.
Right, the printer cartridge. The other interesting thing, is, I mentioned this in my class, you go to Lowe's, every can of paint on the shelf is white.
Right.
There is no mixed paint. And then you hand them the color swatch, and the three colors they put in are yellow, magenta, and cyan.
In different ratios.
In different ratios to get the different colors.
Now they also might add black or add something to make it darker or something like that. They have a dark base and a light base, but generally speaking, that's what they use.
Right. So something interesting happens. If you take the magenta and you add the yellow, so these are the primary subtractive colors, right? Primary subtractive colors. The other colors, the red, the green, the blue, they were primary additive.
Right.
But if you go magenta plus yellow, you end up with
red.
Red, and we're going to talk about why that is. And if you go yellow plus cyan, you get
green.
Green. And if you go magenta plus cyan, you
blue.
Blue. And if you add all three together, you get black, which is sort of a strange thing. We're going to see this. So let's talk about why this happens. All right, and we're going to start with the red one. So I'm going to treat this kind of like a math problem. I'm sure they're excited about that. Magenta plus yellow equals red. How did we get magenta when we added light together? We did, magenta was red
plus blue.
Plus blue. And how did we get yellow?
With blue and red.
No, it was red and green.
Red and green, I'm sorry.
And so somehow that only equals red. So the only color that's going to show up is the colors that are shared in common. So the magenta has some red in it. The yellow has some red in it. So the only thing that we're going to be able to see is the red.
Right.
We could do the same thing with green. We could say, well, hey, yellow plus cyan is green. And yellow plus green was, red plus green was yellow.
Right.
And blue plus green was cyan. So the only thing left to show up is
the green.
The green. You will also notice there are some common things here. You can have, for example, with a red, I'm red-green colorblind, so I often confuse reds and greens. So some reds can be pushed towards that they have a greenish hue to them, and some greens, depending on the lighting, can appear to be bluish as a result of this, because the red washes out. So when the red washes out, you will pick up hints of blue, or when the red washes out, especially if you're colorblind, you'll pick up a hint of a green. And this would work for the others as well, but I like to do the gizmo here. So if I've got cyan and I add it to the magenta, I'm in fact left with that blue. And just like before, okay, I notice I've got a white background, kind of like white paint.
Mm-hmm.
And so if I wanted to take out some of the cyan and take out a little bit of the magenta, you see when I mix that, I'm getting a different shade of blue.
Right.
Right. If I remove the cyan and add the yellow, there's my red.
Mm-hmm.
Same story. Well, I want a different red. Well, then I adjust accordingly to get what I'm looking for. When I add all three, of course, when we add all paints together, what do we get? We get muddy brown, or we get black, theoretically. And as a result, it's because that's what's left. Everything else has been canceled out, right? And so that's color. This is the color stuff that we are familiar with because we've been painting since we were kids.
Right. Everyone knows that yellow plus red equals orange.
Right. And then as a result of that, of course, the light thing is the harder one to think about because we just have white light coming out of our light bulbs. But what if? And I think we did a nice job of showing that with the different colored light bulbs in class during the investigation. So I think that covers additive and subtractive color mixing. So signing off, this is Mr. White.
And Mr. Sadler.